Earth calling thermoclass. Earth calling thermoclass. Come in, thermoclass.
You're not on yet.
Oh,
What's that?
join.
Wait, did you know? What did you do? I gotta go.
I know you do.
No, I'm talking to Chase.
Sorry.
Did you go to your meetings?
Yeah, I did. And I pushed start.
We're not signed in.
Oh. Hey, there's a customer already. There's Megan, where she's trying to connect. Should I go get that other microphone, or you think it worked pretty good the other day?
Looks like only one person logged on right now.
Well, it's 9 minutes before our time.
Yeah.
Thank you. Hey, I thought there was another lamp.
There is. Do you need it?
Well, you're the one to decide that, do I?
No, it doesn't help.
Okay, thank you. Can you hear me? Unmute, Megan, and talk to me. I think I need to move this just a tad. Let's see. Maybe closer. Maybe it needs to be closer. I can't get much closer. No, wait a minute. I want to pin myself, right? How do I do that? Pin video, that's what I want. Yeah. I think I need to turn this more like that. You suppose? I shouldn't have touched that, dang it. I wonder if they can see that. Hey, we got another customer. Mohammed's there. Unmute, Mohammed. Tell me if you can read that okay. Can't hear you.
I can read it okay.
Hey, good. Is that Megan talking?
Yes, it is.
Excellent. And you can read it okay. I wish I could make it bigger. I wonder if I could. I don't know if I can. No, that doesn't really help much. Well, we're just waiting for people to show up, but we were a little early. But we have some excellent students have signed in already. Do you guys have any questions for me before we get started?
Has the lecture from Monday been posted on YouTube yet?
Oh, thank you for asking. We're having difficulty with that. We will get it, but it's not, and that's why you can't get it. It's not on there. Let me remind me to tell the others. Hey, there's another important person. Parker just signed on there. But we will get that YouTube. this business with computers, they all have these little glitches. I don't know if you've noticed. But we're doing the best we know how. Hey, there's Parker. Hey, Parker. Hey,
I,
I'll wave to you. There you go. Well, I hope you guys can read what's on that board. Now, I think you have some homework that's due at midnight tonight, if I remember right. And we'll do I'm going to give you some more homework. I forget when it's due, something like maybe Friday night at midnight, I think. But I can get those grades. Go ahead, say what you want.
I was just saying okay too.
Yeah. And my plan is to post the answers to your homework after you turn it in. And the homework is worth 4 points each time we do homework. But that'll add up. Okay, now let's see. Today what we're going to study is ideal gas law, I believe is what it says there. Hey, we've got some more important people. Spencer showed up, Cameron, and is it Bear? Is that Bear Goins? Is that correct? I don't have you on my list here. Bear Goins. Bear, unmute and talk to me. Bear is not unmuting and he's not talking to me. But I know the rest of these people, Spencer, Megan, Cameron, and Parker. And it's going to be in 2 minutes official blast off time here.
Hello, sir.
Yeah, is that you, Bear?
Yeah, sorry, my internet was cutting out for a second.
Oh, that's fine. Yeah. I don't have you on my list. Did you sign up late or sign up recently?
Yes, I didn't end up getting enrolled until Monday at like 12.
Well, that's
because-
okay. That's good.
Yeah, there was some issues with like the prerequisites transferring over from a different school.
Okay, good. Well, I'm glad to have you.
Glad to be here.
Well, okay, we'll probably get started here. People are still tuning in. There's Aubrey. Hello, Aubrey. Yay. Aubrey is here. Let's see, Megan's here. Parker, Aubrey, Cameron, and Spencer so far. Okay, now the topic is the ideal gas law. I wonder about the book. We talked about the book Monday. Have you people had any success getting the online thermo book? Answer me, somebody. How about Aubrey? Did you get the book, Aubrey?
Yeah, I was able to rent it through Wiley.
Good. And did they give you the secret number so that you can get the online book?
Yep.
And you've been able to pull up the online book and look at it?
Yep.
Well, good for you. Proud of you. How about you, Spencer? Same thing, I hope?
Yeah, I did the same thing. Got it through Wiley. That was the cheapest rental I could find.
Now, did you do rental or did you buy?
I rented
Okay, how much was it? I'm just curious.
uh $42 for 4 months.
That's a deal.
Absolutely.
I like that deal. Parker, how about you? What's the story with the book, Parker?
Yeah, I did the same thing.
You rented it,
Yep, through Wiley.
42 bucks.
Yep.
Wonderful. That's wonderful. Let's see who else we got here. I got Mohammed. How about you, Mohammed?
Yeah, I purchased the box yesterday, but I didn't get the access code. Probably I will get it today.
Okay. All right, good. But today you're going to get the book.
Yeah, I think so.
I think so. Well, if these other students can figure it out, I bet you can. Okay, well, let's see. The topic today is the ideal gas law. Now, it's in your book. Let me see if I can find the page it's on here. Look, trying to find the ideal gas law. If you can find it quicker than me, just tell me. Still looking here. Yeah, I found it. So it looks like page, well, in my book, it's page 46 and 47. 46 and 47 in the book. Now, it might not be on the same page of your book. Sometimes somebody let me know if these page numbers that I give you are different than your numbers, because I don't want you to get confused. But let me write down the 4 versions of the ideal gas law. Now, this is the one that you probably learned. I bet you learned that one. PV equals MRT. How about it? Parker, I'll pick on Parker. Parker, is that how you learned it?
Yeah.
Yeah, probably in chemistry, maybe.
Yeah, I just took chemistry last semester, so.
PV. But see, there's 4 versions of the ideal gas law. And wait a minute, this was wrong. That was wrong. Please correct it. It's a little n. I wrote that down wrong. But I have that right. Now this fourth version, I'm not sure it's in your book. There are 4 versions of the ideal gas law. There they are. And P stands for pressure. And it is in, well, let's do the SI system first. It's in kilopascals. And volume is in cubic meters. That little n is number of kilomoles. It's the number of kilomoles. And the R bar is the universal gas constant. From memory, I think it's 8.314, but I hate to lie to you. I wonder if that's right. 8.314. Oh, gee. Pretty sure that's right. Well, we'll check it here in a minute. But see, that's the universal gas constant. That's in kilojoules per kilogram Kelvin. And that temperature there is in Kelvin. Now those units there, can you see that these will give you kilomoles times kilojoules per kilogram? No, this is wrong. This was wrong. The universal gas constant is kilojoules per kilomole Kelvin. There we go. See, the kelvins cancel, the kilomoles cancel, and you have kilojoules on the right. Now, when you take a kilopascal and multiply it by cubic meters, what you'll get is, well, here, I'll write it for you. You'll get a kilonewton per square meter times meters cubed. Right? Yeah, Pascal is a Newton per meter squared, multiplied by cubic meters. And I tell you what will happen here is you'll get a kilonewton times a meter. Can you see that? That's a kilojoule. So on the left, you have kilojoules, and guess what? On the right, you have kilojoules. So the units work out fine, don't they? Any question on that? I guess you're okay. Now this one here is my favorite. I'm gonna put a happy face on that one. You'll see me use that one all the time. Now the units on that are kilopascals, cubic meters per kilogram. Now this is not the universal gas constant. It is the gas constant for oxygen or nitrogen or water, even water. If you have water vapor that's hot enough with low enough pressure, it'll behave like an ideal gas. But you can't use the ideal gas equation on liquid water or even a mixture of liquid and vapor. But see, this R here is the gas constant for that particular gas. It's a particular gas constant. This is the universal gas constant. I think it's 8.314 from memory, but I couldn't find it a minute ago. Kilojoules per kilomole Kelvin. And then see, this is kilojoules per kilogram Kelvin, and this is Kelvin. Now, when you multiply that, you'll get kilojoules per kilogram. But when you work out these units here, you get kilojoules per kilogram. So it works great. Let me check this and see if this is right. Here's the way it works. The particular gas constant is equal to the universal gas constant divided by your molecular mass. I'm worried that you guys can see that okay. It looks like you can. Now, if you did, let's do air. We use air all the time. But see, this never changes. That's 8.314. And air is 28, I think it's 2897 from memory. I can look that up. Hang on a minute. Air is, says here, air is 2897. I got that right from memory. Here, let me put the units in. That's kilojoules per kilomole Kelvin, and this is kilograms per kilomole. And so what you'll get is, well, I don't know what you'll get. I'm gonna plug it in here. 8.314 divided by 8.314, 2897. I'm getting 0.2869 bloody kilojoules per kilogram Kelvin. See, the kilomoles cancel. And that is correct. From memory, I gave you the right universal gas constant. If you look up the gas constant for air, it's 2897. Wait a minute. It's 2897. Yeah. That's a molecular weight. But the gas constant for air is 0.287. See, they rounded it off. If you look up R for air in the back of the book, it's 0.287 kilojoules per kilogram Kelvin. But that's what I got, and that's correct. Okay, well, good. Any questions so far? This is a bit boring, and I'm sorry, but we got to know how to do this. And you need to know the names of each one of these. Right here, let me pick on somebody. I like picking on Parker. He's a good sport. Parker, you see that little V right there? Give me the name of it, Parker.
Volume.
No, this is volume. That's not volume. This is volume here.
Okay.
That big, Parker, what's that little V?
I'm not really sure.
That's okay. That's fine. You're here to learn. It doesn't bother me that you don't know it, but I want you to know it. I want you to know the name of that. The name of that is specific volume. Here, I'll write it for you. Can you get? Yeah, you can see over here. Little v is equal to a big V over the mass. It's called specific volume. And the units are cubic meters per kilogram. Here, I put my units in brackets. There you go. Now let me pick on somebody else. Pick on somebody else. Yeah, here we go. See that R with the bar over it? Yeah, I'll pick on somebody here. Aubrey, you're a good sport. Aubrey, what's the name of that thing, that R with the bar over it, Aubrey?
Gas constant.
Yeah. But it's got something, it's the
Is the ideal.
And wait a minute, it's the gas constant. There's a word in front of gas constant. It's the gas constant.
Specific.
No. But again, that's no problem. This is called the universal gas constant. Now, it's different than that R there. See that R there? That's the particular gas constant for a particular gas. It has different units. Now, they are related. If you guys will come down here, this particular gas constant is very much related to the universal gas constant. Now, this right here, I mentioned what it was, but I don't know if you guys caught it. Some people call that the atomic weight. I don't like that term. It's really the molecular mass. You're familiar with it. What is it? There's carbon. Carbon is 12. Oxygen is 16. Molecular oxygen is 32. Am I talking your language now? Molecular weight, molecular mass, in chemistry, that's what that M is. See, for air, there's 28.97 kilograms per kilomole for air. Every molecular substance has a different molecular mass. Okay, now there's this equation here. Now this is my second favorite. I'll put a smiley face here, but not as happy as this one. This is my favorite. I never use this one, so you could forget it, okay? But I'll tell you what it is. Now, let me pick on another student here. There's a little M right here. We gotta know what that is. Spencer, what's that little M?
The M, the mass.
That's correct. It's the mass. Good going. Well, as long as I got Spencer, I'll pick on him again. Spencer, what's that little N stand for?
That N is the number of kilomoles.
That is correct. That's good. Let me talk about moles and kilomoles for just a minute. Since we never use this one, well, I'll leave it up there. Now you guys studied moles in chemistry. Mole. You might have forgotten what a mole is, but it's 6.02 times 10 to the 23rd, usually molecules, but it could be something else. That's what a mole is. Now, mole is really a shorthand for gram moles. It's a gram mole. And what is carbon is 12. See, if you have 12 grams of carbon, you have got a gram mole. Now, if you have 12 kilograms of carbon, you have a kilogram mole. Now, I'll tell you what you'd have. If you have 12 kilograms of carbon, did I do that right? I'm a little bit rusty. Is the atomic mass of carbon 12? Is that right? Chemists? Where's my chemists?
Yeah, it's 12.
Yeah, that's 12 because there's an isotope called carbon 14, right? But see that there's not as much of that because it's a very small percentage, right? Carbon 14. But see, if you have 12 kilograms of carbon, here's what you'll have. You'll have 6.02 times 10 to the 26. And if you're just dealing with carbon, we're not talking about molecules, we're talking about atoms. How come I got 10 to the 26 here and I only have 10 to the 23rd there? How come? Because that's a gram mole, and this here, if you have, this would be a kilogram mole. A kilogram mole of carbon. So now you know the difference between a gram mole and a kilogram mole. Now there's also a thing called a pound mole. Pound mole. You can write it out if you want. Pound mole. There you go. But the book writes it as just pound mole. Now, I don't know if you know this, but there's roughly 2.2 pounds per kilogram, right? I know you've heard that before. So you see, you'd have to divide this. You'd have to divide this by 2.2. Here, I'll tell you what you'd have here. See, there's 2.2 roughly pounds per kilogram. Pound masses per kilogram. Okay, so if you divide 6.02 divided by 2.2, what we're talking about, a pound mole is 2.74 10 to the 26 atoms of carbon, for instance. That's a pound mole of carbon. So we've talked to you about pound moles and kilogram moles and gram moles. I've shown you my two favorite ideal gas equations. This one here, that's pressure. And that little guy there is called the molar specific weight. It's called the molar specific weight. No, that's wrong. It's the molar specific volume. That's the name of that. And what it is cubic meters per kilomole. There you go. And I've already told you that one. That's the, let me see if you guys learned anything. I told you guys what that was, but we'll see if anybody listens to me. There's a lot of, how about Stuart? Hey, Stuart, unmute. Are you there, Stuart?
Yes, I am.
Good. Stuart, I told the people what this R bar was. Do you remember what it is? What's the name of it?
It is the universal gas constant.
Good going, Stuart. You are absolutely right. Let me take roll here so I can keep track of who's here. Stuart, where did you go? Stuart Duval, okay. Stuart, were you here Monday? You weren't here Monday.
No, I wasn't.
I'm going to put the Monday's lecture on YouTube. We're having a little trouble doing that, but I want you to watch it. That would be good. Okay, we got Stuart, we got Spencer. Let's see, Spencer's here. Roxana's here. Parker's here, Mohammed's here, Megan's here. Parker's here, Megan's here. What about Chris? I don't see Chris. Aubrey's here. Where is Aubrey? I don't see. Yeah, there's Aubrey. Okay. Well, is that everybody? Aubrey, we got Bear down, and Cameron. Did I have Cameron on? Yeah, there he is. Cameron's here. Megan, Mohammed, Parker, Megan, Mohammed. Okay, Megan, Mohammed, Parker. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Boy, Joe, that works pretty good. If I were you, I would go through these 4 versions of the ideal gas law, and I would know the names of each algebraic symbol. Just pretend that Mr. Griffin is asking you, what's the name of this big V here? And what's the units it's in? And I would like for you to know that. And I showed you how the units are equal on both sides. You should go through and show to yourself that the units are equal on both sides. So there's your ideal gas law. Now we probably should do some examples. Let me do some examples of it. Do you have any questions about the ideal gas law so far? No questions, I guess. All right. Well, one question is, what is an ideal gas and what isn't? Well, I'm going to take a little sip of water right here. And I just swallowed it. And that stuff that I just swallowed is not an ideal gas. It's a liquid. So you can't use the ideal gas law on a liquid or even a mixture of a liquid and a vapor. It's got to be all vapor. That makes sense. And here's the rule. Well, first of all, there are no ideal gases that obey the ideal gas law perfectly. There are no gases that obey the ideal gas law perfectly. Now, some come dang close. For instance, helium. It's one of the noble gases with helium, neon, argon, krypton, xenon. Ring any bells out there? Noble gases? You've heard of those. You've heard of krypton. Well, what do you know about krypton? Let's go with my friend Megan. Megan's don't have a picture up there. Megan, can you hear me?
Yes.
What do you know about krypton, Megan?
I know nothing about krypton. It's been 4 years since I've taken chemistry.
No. I'll give you a hint. It has something to do with a guy with a big red S on his shirt.
Oh, okay, Superman.
Yeah, there you go. Yeah, I forget the story though. Does krypton hurt Superman or does it help him? Do you know? Is it bad for Superman?
I don't know. I don't remember.
I don't remember either, but
I think it's bad.
It's bad. Something bad happens to him?
I think.
I think you're right, yeah. Well, those are, what do they call those noble gases? Helium, neon, krypton, xenon, and argon. They're called noble gases. And they behave pretty good like ideal gases. And the reason is they don't stick together like water molecules. They're not polar. they're not polar. See, a water molecule is polar. It's got an oxygen that's kind of negative and two hydrogens that are positive. And so one, isn't that kind of what a water molecule is? Sort of like that, an oxygen and two hydrogens. So it's got a positive end and a negative end, and it will attract another water molecule. The positive end will attract a negative end on another water molecule. And pretty soon, if you got enough of those, you've got yourself a water drop. You don't have a vapor anymore, you have liquid. And you can't use the ideal gas on the liquid. What do you do if you have a liquid? Well, let me show you that. And I tell you what, we'll come back. Well, wait a minute, we probably should do let me finish my thought here. There are no perfectly 100% perfect ideal gases, but some of them come dang close. Now, the other rule is that all gases behave like ideal gases if you can thin them out enough. What you have to do is I'll just say, if you can thin them out. What I'm really talking about is their density. If you can make the density of your gas very small, see what that does is it separates the molecules. So you can have these water molecules, but if they're far enough apart, they won't glom onto each other and they won't start forming water drops. And the way you could do that is if you make the temperature very hot, that tends to separate the molecules. And another thing, if you can make the pressure very low. So you can take water at very low pressure and very high temperature, and it can behave like an ideal gas. Does that make sense to anybody? Even though it won't, it will not obey these laws perfectly, it'll come dang close. Let's do an example. Let's do it with water. Let me take some water. I'll use this equation here. This is my favorite. And we'll do an example. But these are the two statements about ideal gases. I don't think this is in the book. If you read the book, I don't think you'll see those, but you need to know that. Any questions before I erase that and do an example of some thinned out water molecules? Well, okay, here we go. Okay, now I need some water vapor that's kind of thinned out here. Let me shop around and see if I can find you some. Okay, I'm looking up water vapor here. We need low pressure. So I don't want any of this high pressure stuff. How about maybe 50 kilopascals. Let's suppose you had water. I'm doing an example now. And we're going to take water and we're going to take it at 50 kilopascals. That's pretty low pressure because remember, atmospheric pressure is around 100. Here, take a deep breath. Here we go. Ready? I just took a deep breath. I just breathed in somewhere around 100 kilopascals. 50 kilopascals, that's about what the pressure is at the top of Mount Everest. That's why they have to wear, well, some of the people take oxygen bottles. But I've heard of people going to the top of Everest without oxygen. But they better not stay there very long. It's a killing zone. And now let's take a temperature. Well, now we want it to be hot, so how about 1,000? How about 1,000 Celsius? That's pretty hot, right? Now I'm gonna look this up in the water table. This is table B.1.3. Now I don't know if you have the capability of listening to me, my wonderful lecture here, and pulling up that table B.1.3 at the same time. I don't know if you can do that, but you guys are pretty smart. You students are pretty good with this computer stuff. But later, after this is all over, you could go look it up. I know you can, if you have a book, and several of you said you got the book, you rented it, you can go to this table and you can look up water at 50 kilopascals and 1,000 C, and here's what it says. It says V is 11.75097. Somebody, if you're able to check that, can anybody out there look in that table and check that for me?
I've got it pulled up and I'm seeing the same thing.
Yay! Good for you, Spencer. You found that number, didn't you?
Yes.
Cool. Proud of you. Okay, now that's from the table. Here, let's write a little word table underneath it. And that's the best answer because these tables have been compiled from experiment. They've actually gone out and they've taken some water and they've measured the temperature and pressure and the volume and the mass, and it's correct. That is the best we have. This is called a model. See, the tables are the best model we have. Now, the ideal gas law is also a model. It's a model of reality. And we're gonna do it with the ideal gas law now and see what we get and see how close we come. Well, here goes. Now the P is, let me make some room here. The P is 50 kilopascal. We're going to solve for the V. Now the R, we're going to have to look that up. I don't have that memorized. I never use the ideal gas law on water because I use the tables. I use the best. The rule is use the best model you have. But there is a gas constant for water. You just have to look and find it. Now let me search here. Wait a minute now. Water. Having trouble finding it. There it is. It doesn't say water, it says steam, but it's the same thing. Now that R is 0.4615 kilojoules per kilogram Kelvin. I found that on table A5. A.5. If you're able to pull up that table A.5, you will find that value for the gas constant for water vapor. Now the temperature, it's got to be in Kelvin. Now we said 1,000 Celsius, so that would be 1,273.15 Kelvin. I think we talked about Kelvin Monday. When we get the YouTube thing hooked up, you can watch that again, or you can read your book. But to get from Celsius to Kelvin, you have to add 273, right? And so you can get your Kelvin. All right, now I'm using this formula here. This is the ideal gas law. It's my favorite. There's 4 of them. And now I'm going to solve for the V. Here goes. 0.4615 times 1273.15 divided by 50. Okay, I got an answer. I plugged in this equation and I got V is 11.751 cubic meters per kilogram. Now let's compare that with the right answer. Well, Shazam. You know what? That's pretty dang close. Look at here. The correct answer is 11.75097. But if you rounded it off, we got 11.751. I'm real happy with that, aren't you? I'm happy with it. Now, why did that work? Because that's hot. 1,000 Celsius, that sounds kind of hot to me. And the pressure was 50. That's pretty low pressure, isn't it? So see, the molecules, your water vapor, are spread out. They're thinned out. You've got low density, and you get a very good answer. Now, we probably should do that with your English units. Wouldn't that be fun to do the English units? Let's do the English units. If you understand all that. We're going to do it with English units now, unless somebody has a comment or question. Okay. Well, let me find some numbers here to play with the English units. Let me shop around here and see. And the water table with the English unit. Okay. All right. We're going to do another example now. We just did water vapor, and we use the ideal gas law. See here, let me put a little IG underneath that V. That V we got from the ideal gas law. This little v, the specific volume, we got from the tables. This is the correct answer. But man, that is close. Now we're going to do it with English, unless you have a comment or question. Well, okay. All right, well, here, let's do an example with Inglés, señor. Okay, we're going to do Inglés. Habla inglés. Okay. Well, let me shop around here and find us something. Now, the English tables are in the very back of your book. They have the SI tables first, and then here they are. Here's the English tables. Now let me shop around here and find what I want. Okay, let's have something about half atmospheric pressure. See, atmospheric pressure is 14.7. And so half of that would be, what, 7 something? How about this one? This looks pretty good. We're going to have water. And we're going to have 5.997. No, wait. Just a minute. I'm on the wrong page. Just a minute here. Okay, here we go. We're going to have 5 psi. Keep in mind that atmospheric pressure averages around 14.7 psi. So 5 psi, we're back up on the top of Mount Everest again, okay? It's really, the air is really thinned out. And now let's get the temperature. What about, we want something hot, don't we? You know what? We could have 1,000. Let's have 1,000 degrees Fahrenheit. That sounds good. Okay. So what we have is water vapor, 5 psi and 1,000 Fahrenheit. Now I got a table on the back of this book that's table F.7.2. And it says if you got 5 psi and 1,000 Fahrenheit, the specific volume is 17586 cubic feet per pound mass. And one of my wonderful students, I think it was Spencer, had luck finding the metric specific volume. Spencer, are you able to find that 17586?
I'm seeing 173.86.
Just a minute. I could have read this wrong. You are Spencer, you are absolutely right. My wife keeps telling me I need to get glasses, and I tell her, no, I do not. She also tells me I need to get a hearing aid, and I tell her, no, I do not. Good going, Spencer. Well, that's in the tables. Now, this is the correct answer. This is from the tables. Okay, we did great. Now we're going to do it with the ideal gas law. Well, here goes. Let's see, the pressure is 5. Now, a PSI is a pound force per square inch. That's what it is. That's what PSI stands for. It stands for pound force per square inch. And then there's the little v. We're going to solve for that in a minute. Can't use that R we did before because this is English, senor. So we're going to, I'm going to have to dig and find the R. That R has a name, by the way. It's called the gas constant. In this case, for water. So let me shop around and see if I can find it. Here we go. All right, I'm shopping around here. I don't see it. Let me keep looking. Hey, I think I found it. Here we go. It's I'm putting this R in here, and I'm getting 85.76 foot-pound force per pound mass Rankine. That I found that on table F.4. I found it on table F.4. Make sure you can find it. That's the gas constant for water vapor in English units. And then I have to put the temperature in there. Now the temperature 1,000. Yeah, but it's got to be in Rankine. So it's going to be 1,000. Oh, gee. Trying to remember the number. Is it 459? 67? Did I do that right? Let me make sure that's right. I talked about this Monday to get from Fahrenheit to Rankine. Let me see if I did that right. A little trouble here finding that. Okay, temperature. Boy, Jove. That's the right answer. By the way, if we talked about this Monday, but to get from Fahrenheit to Rankine, you got to add 459.67 to it. And I found that on table A.1. If you want to know, well, where did he find that? It's in table A.1. Okay, now here's the equation here. But now here's a problem. I talked about this Monday. These units aren't going to work out. See, these are going to be foot-pounds per pound mass. These aren't. Because, see, that's going to be cubic feet per pound mass, and you're going to have pound force, cubic feet per pound mass, inches squared, and that's not the same as what you have over here. But you can make it the same by doing this. If you don't do this, you'll just wind up with the wrong answer. But see, now you're going to have foot-pounds per pound mass on the left, and you'll have foot-pounds per pound mass on the right, and it works out. Okay, well, here goes. I'm gonna solve for V now, and I'm using the ideal gas law now. Okay, well, here goes. Let's see, 85.76 times 1459.67 divided by 5 divided by 144. Well, I got an answer. Don't have much room, but in my calculator, I got an answer for the specific volume using my ideal gas law. I'm getting 173.86 cubic feet per pound mass. Well, boy, Jove, that's precisely what we got. It worked out good, didn't it? It worked out good because I purposely picked some thinned out water vapor, very low density, high temperature, low pressure, and the ideal gas law worked pretty good on that. I mean, I got exactly the same answer. Do you have any questions on that? I sure wish some of you would ask me a question sometime, but I would feel more confident that you're getting this, but maybe you're getting it. I'm hoping. Okay, next topic. We're gonna move on to the next exciting topic, unless you have a comment or question. All right. Well, I showed you the ideal gas law in SI and also in English. And now we're going to talk about the next topic. The next topic is something called compressibility. The symbol for it is Z. And here's where it comes from. It comes from these 4 versions of the ideal gas law. All I did was I took the 4 versions of the ideal gas law that we wrote earlier, and I put this Z thing. It's kind of a fudge factor, what it is. What if you have something like water vapor, but it's not real low pressure and it's not real high temperature? What if it's such that the ideal gas law gives you a bad answer? I'm going to show you how to do it. See this thing here? You can get a better answer. Let me show you an example of this and how you this is called the compressibility factor. They use the symbol Z for it. Okay. Now here's an example. We're going to take water again, but we're going to take 6,000 kilopascals. Gee, that's bigger than atmospheric pressure, isn't it? See, atmospheric pressure is what, 100 kilopascals? Well, gee, that's 60 times atmospheric pressure, isn't it? Yeah, 60 times 100 is 6,000, right? I think so. Man, you wouldn't live very long if you were in a room that had 6,000 kilopascals. Of course, you'd die because there's no air in there if it's all water vapor. And here's another thing that would be uncomfortable. Suppose it's at 300 degrees Celsius. Well, that'd burn you, wouldn't it? I mean, you got 2 things that are going to be uncomfortable. The pressure is so hot or so high that it would just squeeze you down to a blob, and the temperature would roast you. It'd be dead quick. But we're going to calculate this. Now, I can look this up in the tables. Now, those of you that have figured out how to get the tables on there, I think I'm going to shut up for a minute and a half and see if anybody. Now, I know Spencer can do it, but I wonder if anybody else can. see if you can find your water tables. I could even tell you which table to look in. Let me see if I can find it. If you have access to the tables, and you must have access to these tables, this is table B.1.B.1.3. I'll be quiet now for a minute. See if anybody can find the specific volume of water vapor at 6,000 kilopascals and 300. Oh, wait a minute. Yeah, 300 C. You can do it. It's right there in the table. I'll be quiet. How about Cameron? I haven't called on Cameron. Cameron, are you? You're my old student that I've had before, aren't
Yes.
you? Yeah. Well, Cameron, are you able to find this table B.1.3 and get the specific volume?
Yeah, I just got the table pulled up. I haven't found the number yet.
You keep looking. See if you can find it. We want 6,000 kilopascals and 300 C. Can you find it, Cameron? What'd you get?
And is it 0.03
Yes, 0.0361.
616?
Good going. Now those are cubic meters per kilogram. Good going. So I know two of you can do this. You must all be able to do this. Let me count my students. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. I've got 9 wonderful students on board here. 1, 2, 3, 4, 5, 6, 7. Yeah, we're missing one, but hopefully we'll get this lecture on YouTube so you can watch it. Okay, now we did that with the tables. Now I'm going to do it with the ideal gas law. Now there's with the Z thing thrown in. Do you understand? See that Z? I need the room here. Let me erase this for right now. I'll erase that. We're just going to use this one here, and we're going to try to do it. Well, now first of all, we're going to do it with just the ideal gas law, PV equals RT. Then I'm going to show you how to find this Z thing, okay? But first we're going to do this. So here, let me plug in the numbers. Now, what do we got here? 6,000 kilopascals times your little v equals, oh gee, I wish I hadn't erased that. Anybody taking notes? What was the R? Does anybody remember? Am I going to have to look it up? I'm going to have to look it up. Nobody's saying anything. Okay.
I think the R was 0.4615.
Yeah, good going. 0.4615. Good going. but not that I don't trust you, but I'm going to make sure that's right. And looking that up in the book there. Yep, that's it. It's in table A.5. If you want to look up table A.5, there it is. Okay, now the temperature. But you have to add the 273 to it. So it'd be 573 Kelvin. And now we're going to find the specific volume. Here goes. Okay. 0.4615. 0.4615 times 573.15 divided by 6,000. I'm getting 0.04408 something cubic meters per kilogram. Well, we're way off, guys. You know what? We're way off. 0.044. This is the correct answer. We'll put a happy face on this one. This is the correct. The tables are the best model. This has really let us down. Let me tell you the percent error. Here's how you could get the percent error. Take 0.4408. Subtract 0.3616 and divide by the correct answer, 0.3616. And to get the percent error, you have to multiply by 100. All right, let me get the percent error. Here goes. Take that, subtract 0.03616, 0.03616. I'm getting 21.9% error. We are 21% off. Can you read that? Hope you can read this stuff. We're off by 21-something% using the ideal gas law. But now we're going to find this Z thing. They call it the compressibility factor. And we're going to get a better answer, okay? But now I'm going to show you how to get the compressibility. I need this room here. So let me erase all this. We got our answer. Now this answer here is using the ideal gas law. And it's way off. We're unhappy with that. How would you like it if on your paycheck it was 20% off? Well, it'd be okay if it was 20% off on the positive. You wouldn't be too upset. But if it was 21%? I forget. 21% off negative, you wouldn't be very happy. Hey, what happened to my 21% on my paycheck? Okay. I'm going to erase this. I hope you guys are taking notes because I need this room here to find this Z thing. There's quite a bit of room right here. I bet we can do it. Now this is how you to find the Z, to find the compressibility. The name of it is the compressibility factor. It's a different model. This is our third model. We have the tables, that's a model. We have the ideal gas law, that's a model. And this thing here is called the compressibility model. And the first thing you have to do is you have to find the critical pressure and the critical temperature for water. How am I going to explain that? I'll explain what that is later. But the The critical pressure for water. Well, there's actually two ways of finding it. If you go to your tables, your water vapor tables, you'll see that the biggest number on there is 22,089 kilopascals, and the biggest temperature on there is 374.14 degrees Celsius. Now I found those numbers on table B.1.2. But let me show you another place you can find them. There's another place you can find those, what they call the critical values. Trying to find it here. Yeah, here we go. On table A.2, it says for water. Are we doing water? I just had a senior moment. I think we're doing water. And it's, yeah, here we go. It says the critical pressure is on this table here, A.2. They say it's 22.12 megapascals. I can't help it that their number doesn't really jive with that number, does it? That kind of bothers me a little bit, but that's what the book says. Now let's see what the critical temperature is. They say it's 647.3 Kelvin. Well, see, that's in Celsius. What would you get if you added 273.15 to that? Let me just see what you'd get. 374 plus 273. I'm getting 647.29. Hey, that's right on the money. I'm happy with that. When you add these, you get 647.29. We'll round it off to 0.3. I don't know why those are slightly different. The book could have made a tiny mistake. It's possible. But that's your first step. To find compressibility, your first step is to find what they call the critical pressure and the critical temperature, which I'm going to explain better later, but not right now. Now the next step, here comes the next step. You have to find what they call the reduced pressure and the reduced temperature. These have names. This is called the reduced pressure. This is called reduced temperature. And what this is it's your pressure divided by your critical pressure. And what this is your temperature divided by your critical temperature. Okay, well, our pressure is actually 6 megapascals, you know it? And so if you take 6 megapascals and divide it by 22. I'm just going to go 22.1. 6 divided by 22.1. Did you get 0.27? Now I'm going to find what they call the reduced temperature. I'm going to take my temperature, which is, oh, but this has got, wait a minute, this has got to be in Kelvin. Isn't that the 573.15 Kelvin? And so you take the 573.15 Kelvin divided by the critical temperature, which is 647. Okay, here goes 573.15. You divide it by the critical temperature. You guys could read this in the book. The book tells you how to do this, but I'm getting 0.89. It's really 0.885. I'm just lazy and rounded it off to 0.89. We're almost done now. We're finding Z. It's called the compressibility. I call it a fudge factor. It's going to give us a more accurate answer than just using the ideal gas law. Remember, the ideal gas law, we were 21% off or 22%, something like that. We're going to do better with this Z thing. We're at the last step now. To find Z, first you find the, what do they call these things? Critical pressures and temperatures. Then you find the reduced pressures and temperatures. Well, we did that. This is the last and final step of finding Z. And what you have to do is you have to go to a graph. This graph is on page, in my book, it's on page A77. Now this is going to be ugly and nasty, and you guys probably aren't going to like this. Now I need some room to operate, so there's a little space right here, so we'll work in this little space right here. Okay, now here's what we know. We know the reduced pressure is 0.89. I hope you guys followed that. We can go back over it if anybody wants me to. And the reduced temperature is, wait a minute, I did that wrong. It's 0.2, the reduced pressure is 0.27, and the reduced temperature is the 0.89. There we go. Now we're going to go to a table. This is figure D.1. In my book, it's on page A77. But I don't know if you have the same page numbers on your ebook. I'd really appreciate it if somebody would make a note of that and inform me if it's on the same page. But here, I'll hold up this this graph. We're going to get Z off of this graph. Oops. Yeah, here we go. You see this? I'm wiggling my finger here. There's a graph here. It's where I'm wiggling my finger here. This is the graph we got to find, this Z thing. If you don't have this graph, you're going to have trouble finding the Z. Okay, now what I'm going to do is I'm going to go to 0.27. Well, I'll tell you where that is. There's 0.01. There's 0.1. Oh gosh, you guys can't, there's no way you guys can see that. You'd have to have your own graph in order to see it. There's 1. Now 0.2 is in between 0.1 and 1. We want 0.27. That would be pretty close to 0.3, actually. So there's 0.01, or there's 0.1, there's 0.2. That would be 0.3. I'm about there on the pressure. Now the temperature is 0.89. There is a 0.85 and there's a 0.9. I think the closest is 0.9. Well, we're going to call that 0.9. So here's 0.9, and it comes up here, and it goes scooting over, and it crosses 0.3, 0.9. It's really 0.89, and it's not quite 0.3, is it? It's you come over here to read the Z, I'm getting 0.8. Let me stare at it another minute here, but I'm getting Z is 0.8. You really need this graph. It's a figure D.1. In my book, it's page A77. And let me do it carefully. If reduced pressure is 0.27, yeah, I know where that is. And you come up here, and we want 0.9. 0.27, 0.9. I'm changing my mind a little bit. It's more like about 0.84, guys. I was holding that up there and kind of hard for me to read. I think it's a little closer to 0.84. Well, good luck reading that graph. And now we're done. We found our Z, and now we're going to find our answer using this equation here now. This is our third model. We have the tables, we have the ideal gas law, and we have the compressibility. And what we're doing now is we're going PV equals 0.84 RT. And we're going to plug in our numbers, and we're going to get a better answer. Now P is, we're doing, if you tuned in late, don't know what we're doing, we're finding the specific volume of water vapor at 6,000 kilopascals and 300 degrees Celsius. That's what we're doing. And we did it with the ideal gas law, and we were off by 20%. But now we're doing it with the compressibility. Now this is 6,000 kilopascal. There's our V that we're going to find. There's the Z to the best of my ability. Oh, gee, and I've erased it now. It's 0.4 something. Somebody help me with that. Was it 0.46 something? Anybody remember?
0.4615.
Very good. Thank you so much. 0.4615 kilojoules per kilogram Kelvin. And the temperature, well, we have to put it in Kelvin. It's in some room here. It's 573.15 Kelvin. Okay, now we're going to solve for V. Here we go. And we're going to get a better answer because this is a better model. Okay, here goes. 0.84 times 0.4615 and 573.15 divided by 6,000. Okay, I got an answer, guys. Here's what I'm coming up with. I'm coming up with a V of 0.037 bloody bloody bloody. Now let's get our percent error this time. And you understand this is the correct answer here, the 03616. This answer here that we're getting, let me put a little Z under that. This is the answer that you get when you use compressibility. Okay, now I'm going to get the percent error. Here goes. Percent error will be 0.03 blah, 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 minus blah, 03, blah, 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 and you divide by the correct answer. That's how you always do percent error, right? You divide by the correct answer, times it by 100. And here goes. I'm going to see what we get here. Let's see. Minus 0.03616, 0.03. I goofed up here. This is 03616. There, I got that right now. 03616. Boy, Jove, I'm getting 2.4% error. Hey, that's better than 21% error. It's 2.4% error. So in other words, on your paycheck, they had to take out 2.4% for health insurance or Social Security to pay old guys like me or something like that. But you can live with that, can't you? Better than 21%. Any questions on that? We just showed you how to do that with finding the compressibility. Now, we need to practice this stuff so that you'll know how to do it. So we're going to take a little 10-minute break here, and then we're going to come back, and I want to practice this stuff with you guys. But aren't you sick of this? Don't you need a little tiny break? Maybe some of you go turn on the coffee pot or whatever you do. All right, I'm just going to leave everything on here because I don't want anything to go away. And we'll practice this stuff here in about, well, I got roughly 10 o'clock. At 10:10, we're going to be back and we'll have more fun, okay? Go stretch. Stretch, get a drink of water or something. We'll be back. 10:10, all right. Hey, Jeannie. Hey, you should see how much water is in the pool. Oh, it's about a third full. They're having a 10-minute break, but we're going to start right now. It's time to start. I've been kidnapped. Okay, honey
I'm
child.
leaving to go see boys.
Okay, you go have fun.
And Chase and Rebecca are gone to buy more pool supplies.
And Gabriel's down
And
there.
Gabriel's down here.
Okay.
And he will only interrupt you if it was an emergency.
Okay. Okay. Well, our 10 minutes is up and we need to see if we can actually do this stuff. All right, I'm going to see if you guys listened to any of my talk there. I'm going to erase all this stuff. We know it's June 3rd. We know it's Wednesday. And there's some homework. If you'll go to Blackboard, well, there's some homework due tonight, and then there's some new homework. I think it's due Friday night. Yeah, that's right. What is the new homework? I think it's maybe 262 and 2110E. Go to Blackboard. Go to your schedule. I need somebody to tell me that they can find their homework.
I'm looking at it, and
yeah.
it says that the next one says it's due Monday.
Oh, okay, I was wrong, but it's due Monday. It's not Friday. You are right. It's due Monday. Good going. Thank you for mentioning that. But is it what I said, 262? Probably.
Yeah.
Yeah.
And 110E.
Good. Yeah, there's your homework. And that you don't have, don't start on it now. When is it due? Monday at midnight? So you need to start on that about 10 p.m. Monday. I don't know, maybe that's cutting it a little close. Okay, here's what we're going to do. We're going to go to the ammonia table. I'm going to work you through a problem. Is there 2 M's in ammonia?
Pretty sure it's just 1 N.
Karen, how do you spell ammonia? It's 2 M's. Whoever said there's 1 M, spank yourself. My wife's a good speller. Well, you know what? We could probably look in the book. I bet you it tells you how to spell ammonia in the book here. Let me see. Yep, 2 M's. That's what the book says. Now let's suppose we had ammonia at 1200 kilopascal and 50 degrees Celsius. First thing I want you to do, I'll shut up for 60 seconds. I want you to find the specific volume from the table. Go to the back, snoop around, find the table. I'll shut up for a minute. See if you can find it. Okay. Let's ask somebody that we haven't asked for a while. How about my friend Roxana, were you able to find that?
I'm still looking for it.
That's fine. Keep looking. That's fine. Let me pick on, because see, I need to know what you guys can do. How about my friend Parker? Parker, can you find that?
Is it 0.11846?
That's what I got. So we're doing good. Okay, now now we're going to find we're going to go PV equals RT, but to do that, we got to know what this R is. So I'm going to shut up for a minute, 60 seconds. I want you to find R for ammonia. Dig and see if you can find it. R for ammonia. Ideal gas constant for ammonia. I know you can do it. Parker, do you have that yet?
Not yet.
That's fine. Keep looking. It's table A.5, Parker. Aubrey, do you have that yet?
Is it 0.4882?
Yeah, that's what I got. Okay, now we've got to get that temperature in Kelvin. I'll shut up for a minute. I need that temperature in Kelvin. Find it. I can't do it in my head. Mohammed, do you have that temperature in Kelvin for us?
I think 323.
Yeah, that's what I got. Okay, now let's see. We got the temperature, we got the R, we got the pressure. Now I want you to solve it, and what we're going to do is we're going to get the specific volume from the ideal gas law. Plug in the numbers. Look here. When I circle something in this class, it means we got it. We got that. We got both of those. We got that. We ought to be able to find that little V there if we know all the rest of it. All right, go ahead and do it. I'm going to do it. Well, I got an answer. What about Megan? Megan, I forget if I picked on you today or not.
You have just a little bit, but I got 13.147.
Well, now Megan, I got 0.13147.
Okay.
You said
Yeah, I must have not moved my decimal places for.
yeah, okay. Well, be careful about that. All right, now you'll notice that we're way off here. This is the correct answer, and this is way off. But now we're going to do it with the compressibility and get a better answer. Okay, so here we go. Now to do it with compressibility, first of all, we have to find the critical pressure and critical temperature. Again, I'm going to give you a minute. I want you to look those up, and I'll be quiet. I want you to find them. Right now we're trying to find the critical pressure and the critical temperature. I showed you two ways to do it. One way is table A2, A.2. Well, I got what I think are the answers. Now let's see. How about Cameron? Cameron, do you have the critical pressure and critical temperatures?
Not yet.
Okay, take your time. There's no hurry. Let me pick on Bear. My friend Bear. Do you have that?
Do you want the ones from table A2 or?
Yeah, that'd be good. That'd be fine.
Okay, what I found for the critical pressure for ammonia is 11.35.
Good going. That is good.
And then the temperature is 405.5.
Good. Excellent. Good going. Now, another way of finding that, Bear, is by going to the ammonia table. Let's see if I can find the ammonia table in the back here. And you can find that it's the last number in the table. They have 11,333.2 kilopascals, which is dang close to this. Again, it's slightly off. Now they have the temperature in Celsius. I'm on table B2. You can find these on table B2, but they have 132.3. But see, if you add to get the Kelvin, that comes out to be right on the money, 405.5 if you round it off. So you can get these numbers. I think they're being a little sloppy on that number there. They're a little bit off, but I would go with the tables. table B.2.1, B.2.1. But you can also use, what is it? Is it A5? Is that what you guys said? Yeah, no, A2. You can get those answers from table A2 or from table B.2.1, and you'll be fine. Okay, good. So far, so good. All right, now we're going to get what they call the relative pressure. That's PR. And the relative temperature, that is TR. Now what this is your pressure divided by your critical pressure, and this is your temperature divided by your critical temperature. I want you to find those for me. I'll be quiet. I want you to see if you can find the relative pressure and the relative temperatures. See, we know what the temperature is, and we know what the critical temperature is. There's critical temperature. And we know what the temperature is, don't we? Yeah, there it is. Yeah, we got the temperature. We got the critical temperature. Okay. Well, I wonder, I've got them. I've got what these are. Relative pressure. Let's see. Spencer, haven't called on you for 10 minutes. Spencer, do you have either one of these? Relative pressure, relative temperature? Spencer?
Yeah, for pressure, I have 0.1057. And for temperature, I have 0.7969.
Now, I like the 7969, but I got something different for the pressure. See, the pressure, that's in megapascals. So you're going to have to put this, in megapascals. You have
Right,
to go,
which it's
it'd be
1.2 over
1.2
11.35.
divided by 11.35, right? So what
Yeah, and
is
I
it?
got 0.1057.
Well, maybe you're right. Maybe I was wrong. You know what? My apologies. I think you did it right. I think you did it right. Okay. Great. Now we're going to go to the. We're almost done now. See, there's these little processes you have to go through. Now the last step is you have to find this graph. And you have to read this graph. Now let me find it again. And by the way, that was Spencer, and Spencer was right, and I think I did it wrong. So I'm going to give him a little thank you point up here in the corner. And I appreciate it when you guys, it helps the class that way. Okay, now we're going to go to this figure D.1, figure D1. It's in the back of the book. I was showing you guys that. See where my finger is wiggling over here? It's this crazy looking graph. This is what you have to use to find your compressibility. All right. Well, I'm going to do it now. Let me get my sharp pencil here. And I'm going to go to 0.1, 0.105. Well, that's dang near just 0.1. There's a big old thick line there, and I'm on it. Now the reduced temperature is make it 0.8, guys. Just say it's 0.8, okay? Now there is a 0.8, and it comes up here, and it crosses that 0.1 about, I don't know, about 0.93 maybe. Guys, I'm getting Z is equal to somewhere around 0.93. Those of you that have that graph, you see that 0.8? Let me show you what that 0.8 is doing. There's a 0.8, there's a dashed line, and it comes up here, and then it takes off this way. And then down here someplace is the 0.1 line, and they cross. This is the 0.8 reduced temperature line, and this 0.1 is the reduced pressure line. And they cross right there. And if you go over here and read it, I'm getting a Z of around 0.93. Does anybody out there agree with me on that? How about Stuart? Stuart, are you able to find this graph and find where they cross, Stuart?
Yeah, and 0.93 sounds about right.
It sounds about right. All right. Well, we're gonna find the improved answer now. If all of that made sense to you, I just need some room to work here. Okay. Well, I'm going to make some room so I can work. Here we go. I need the room. What we're going to do now is we're going to go PV equals ZRT. And the P is 1200 kilopascal. The V we're going to find. The Z it's somewhere around 0.93, somewhere in there. And the R is 0.4882. And then the temperature is, oh gee, did I lose it? I lost it. Just
I think it's 323.15.
Yeah, good going. 323. Thank you so much. Okay, now we're going to solve this for V. Here we go. 0.93, 0.4882. 323.15 divided by 1200. Okay, I'm getting a 0.1223 cubic meters per kilogram. All right. Now, this is using compressibility. Remember, this is your correct answer right here. We'll put a little happy face by it. That's from the tables, 0.118. This is from using the ideal gas law, it's 0.13. This is using compressibility, it's 0.12 something. Well, let me get the percent error. Here goes. I'm going to find the percent error here on this one. Just let me do that. 0.13147. 0.11846 divided by 0.11846. Not too bad. It's around 11% error using the ideal gas law. Now we're going to find the percent error using compressibility. 0.1223 minus 0.11846 divided by 0.11846. This is 3.2% error. Hey guys, 3.2% error is better than 11% error, isn't it? Oh, yeah, it is, Mr. Griffin. Well, see, it's an improvement. So we have done that with you, and you hopefully understand the ideal gas law. Now, what would be fun would be to do that with some English units. See, that was all with metric. We've got to know English too, but we'll get to that and do that soon. But I want to talk to you now about what the heck this critical this and critical that. What does all that mean? So unless there's a question or comment, we're going to go on and we're going to talk about something else. But I'm open for any of your questions. Well, nobody seemed to say anything, so we're going to talk about, let me make some room here. I was telling you guys Monday, I think I mentioned superheated vapor and compressed liquid and saturated mixture. We're going to be studying something called a PV diagram. It's probably the most important concept in the course. And if you have something like water or ammonia or some of your refrigerants or 100 other things, propane, you name it. In this region here, they have what they call saturated mixture. It's saturated mixture. It's got liquid plus vapor. Now out here, it's all vapor, and they have a name for it. They call it superheated vapor. And being lazy, they just write it as SHV, superheated vapor. Now over here, everything in this region is called compressed liquid. It's all liquid. There's no vapor at all. Here you got a mixture of liquid and vapor. Here you have nothing but vapor. Now the very tippy top right here is called the critical point. we were looking that stuff up. Like for water, just from memory, it's around 22 megapascals for the critical point. But here, go to your water table and I'll show you. If you go to your water table, at the very top of the table, they have 22,089. It's actually 22,089 kilopascals. I can just remember 22 megapascals from memory. Now they also have a what they call a critical specific volume. Now what it is from the tables is 0.00315 cubic meters per kilogram. So there's a critical specific volume and there's a critical pressure. See, that's the critical pressure. But there's also a critical temperature. Now, I like to put my isotherms in red. And the critical temperature does a weird thing. It does this. Comes down here. And it goes like that. This is, I don't know if red shows up very good on your computers or on your cell phones there, but I'll make it nice and thick. This is the critical temperature. Yeah, there you go. That's nice and red. That looks pretty good. See, this is called the critical isotherm is the fancy name for it. It's an isotherm. Iso means the same in Greek. And it's the same temperature. Everywhere on this isotherm is the same temperature. And that temperature is 374.14 degrees Celsius, according to the tables. I'm on table B.1.2. The temperature here is 374.14 degrees Celsius. Guess what the temperature is here? It's 374.14 degrees. It's an isotherm. Everywhere on there has the same temperature. Now there's other isotherms in here. There'll be another isotherm in here that at 300 degrees. Let's see if I can find it. Yeah, there it is. 300. Again, it should be in red, but there's a 300 degree isotherm. It does this. See, these are cooler. And it does a weird thing. It's flat right here. It's perfectly flat. And then it does this. Whoops, maybe got too close, but that's okay. Well, they don't merge. They're different. That's your 300 degrees Celsius isotherm. Everywhere on here is 300 degrees Celsius. This is 300 degrees Celsius. And everything here is 300 degrees Celsius. Now, if you wanted maybe 100 degrees Celsius, we could find it. But let me show you something interesting. The pressure there for the 300 degrees Celsius, according to the tables, is 8581. This is 8581. kilopascals. And what happens in here is if you're going to the right, that's called boiling. So you're starting with a liquid right here. It's all liquid right there. And you're going to here, put an arrow here. That's all vapor right there. And when you go from a liquid to a vapor, isn't that boiling? Now, another name for it is evaporation. If you go to the right, it's called evaporation. If you go to the left, if you go from a vapor to a liquid, going to the left, does anybody know what they call that when you go from a vapor to a liquid? Earth calling student.
Condensation.
Yeah, that's it. It's condensation. For instance, if you take your ice cold Mr. Pibb or Dr. Pepper or whatever you like. My grandson likes something called a fizzy. Have you ever heard of fizzies? Well, never mind. Coke. You got a bottle of Coke, and you set it on your mother's nice coffee table. And after a few minutes, if you lift it up, you'll see a ring of water down there on the coffee table. That's not good. You could wreck her finish on her furniture. It condensed. See, there's water vapor in the air, and it hits that cold Coca-Cola bottle, condenses on it, and it goes from a vapor, from a water vapor, which is all a bunch of separated molecules. They condense, and you got yourself a little pool of water there on the table. It's condensation. Okay, well, great. That's how those isotherms go. Now, what do we do when we're in here? Oh, by the way, this line right here has a name. This is called your saturated vapor line. And the symbol for that is S dot V. Saturated vapor. This line right here has got a name too. It's called the saturated liquid line. And the symbol is S dot L. Compressed liquid has a symbol as CL. Saturated mixture is S dot M. Saturated vapor, superheated vapor, critical point. Anything out here is called a fluid. It can never liquefy. Do you understand? It's always anything out here is always a vapor. Can't liquefy. Now there is a place down here, if you're cold enough, you get below zero, you can have a solid. You can have a solid. Well, you can have ice. But what I want to talk about now is your specific volume when you're in here. That's the topic. And the topic, it's called quality. And the symbol is X. You probably should read your chapter. They explain this pretty good. But we're going to talk about in here. Like, suppose you're right in here someplace. Well, it's got specific volume. It has temperature. It has pressure. And I'm going to try to explain it. Let me say goodbye to all this for just right now. Anytime you have a question, just ask me. What I'm talking about right now is something called quality. The symbol is X, and what it stands for is the mass of the vapor divided by your total mass. That's what quality is. It's a percent vapor is what it is. And it's something that occurs in the saturated mixture region. So let me take a closed vessel like this. No, there's no openings, nothing can get in or out. And let's put some liquid down here in the bottom. There's some liquid. And then we're just going to have vapor. Some little molecules flying around in here. You have vapor. You have liquid and vapor, so you have a mixture. Now the total volume of our container what I'm trying to do with you guys is I'm trying to come up with this formula right here and trying to explain it to you. See, we've shown you how to find specific volume in the tables. We've shown you how to find specific volume using the ideal gas law. We've shown you how to find specific volume using compressibility. And now we're going to show you this equation here to find the specific volume inside what I call the vapor dome, where you have a mixture of liquid and vapor. See, there's some liquid here. See, there's some liquid, and here's some vapor. That's supposed to be a P, not an R. But here's my thinking. The total volume of this container should be the volume of the liquid plus the volume of the vapor. That makes good sense to me. How about you? Total volume. Does that make good sense to you, Spencer? Total volume of this container should be the volume of the liquid plus the volume of the vapor. What do you think, Spencer?
Makes sense to me.
It makes sense to me, too. Now here's the thing. That total volume should be the total mass times the total specific volume. That volume of the liquid should be the mass of the liquid times the specific volume of the liquid. That volume of your vapor should be the mass of your vapor times the specific volume of your vapor. Try to remember what specific volume is. It's volume divided by mass. And so volume should be mass times specific volume. That's how come you're getting mass times specific volume. Mass times specific volume. So far, so good. Okay, now we're going to do some algebra now. I'm trying to show you this formula here that you use when you have a mixture of liquid and vapor. You can't use the ideal gas law. And you do have to use the tables, but without this equation, you can't use the tables. We got to know how to use the tables. All right. Now I'm going to do some algebra, see if you can follow this. I'm going to divide this by the total mass. I'm going to divide this by the total mass. I'm going to divide this by the total mass. Now that's legal. When you take algebra, and you do stuff to both sides of an equation, it's perfectly legal, isn't it? Hey, when you have total mass divided by total mass, that's just a 1. They just kind of cancel out. So you get the total volume equals the mass of the liquid over the total mass times the volume of liquid. Now they have in the tables, if you go to any of the tables in the back, you'll see this little VF thing. You could think of it as fluid if you like. I don't really like it. But what that is the specific volume of your liquid. And this, look at here, you know what that is? That's your quality. Remember what quality is? It's the mass of the vapor, not var. I didn't do that right. That's supposed to be a P. Guys, correct me if I make a mistake. If you take the mass of the vapor divided by the total mass, you get your quality. And this here, in the back, they've got a little VG. That VG is the specific volume of your vapor. They have pages and pages and pages of VG in the back. You get your book out and look sometime. That's just pages and pages of it. Okay, we're almost done. We're almost done. Now, let's suppose your X was, remember that the PV diagram where you had this goofy thing here, and I was over in here someplace. Let's say you're way over here close to that edge. Let's say you had an X of 80%. You know what that means? That means you're 80% vapor, and mostly vapor. Very little water, mostly vapor. Well, if your percentage of vapor is 80%, the percentage of vapor, if it's 80%, what would be the percentage of liquid? What do you guys think? If you have 80% vapor, what do you have of liquid?
20%.
Yeah, 20%. You betcha. You'd have 20%. So you guys see this mass of the liquid over the total mass? What that's going to be is a 1 minus X. So if you take 100% minus 80%, you'd get 20%. So here we have our equation, and we're almost done. And I've shown you where this equation comes from. And we don't need to put total. We already know that's the total. There's your equation. Now this equation is the same as this equation. There's just an algebra trick there. Take 1 times V sub F and you get V sub F. And this is minus X times V sub F plus X times VG. Well, this thing right here, they've subtracted for you. Here, you could write it like this if you want. They've gone ahead and subtracted that for you and called it VFG. But if you take minus X VF and a plus X VG, that's what you get. But they write it like this. Where they've just subtracted for you. So we have just come up with a lovely equation for specific volume if you have a mixture. Shall we do an example of that? Any comments or questions? Okay, we'll do an example of that. All right, here comes an example of that. I just need some room here. There's our equation. These are the same. And now you know what quality is. It's the percent of vapor that you have. That's what quality is. If your quality is 80%, that means you got 80% vapor. But let's suppose you had water. I'll just make up an example at 2,000 kilopascals. And suppose your quality was 80%. We're going to find your specific volume. Now we got the equation. Go to your table and shop around and find 2,000 kilopascals. They have a table of water that's got kilopascals in it. It's table B.1.2. Can you find it? Here, I'll draw the PV diagram for you. You will discover that the PV diagram is the secret to success in this class. And they kind of look like that. And 2,000, it's down here pretty low. 2,000, because remember, the top is 22,000 kilopascals. So 2,000 is way down lower. However, they're not linear. The scale on the pressure and the volume are logarithmic. See a linear scale, here's how a linear scale works. It goes 1, 2, 3, 4, blah, blah, blah. That's a linear scale. But see, a logarithmic, I'll just abbreviate it. I can't spell logarithmic. I'll just abbreviate. It goes 1, 10, 100, 1,000. See, it's not linear, is it? 1, 10, 100, 1,000. That's not linear. It's logarithmic. And that's what these scales are. See, 2,000 is there. Well, if that's 2,000, 4,000 should be here, and 12,000 would be here. Man, that's not linear. It's 22,000 there. So that's okay. We can live with that. Now we're going to look up this little thing right here. This is called VF. And if you have that table, B.1.2, you will find out that VF is 0.001177 on table B.1.2. And this little value right here on the other side is VG, and it is a 0.09963. Now I'm going to shut up for 30 seconds, and I want to make sure that you can find that. See if you can find those of you that know how to get to the tables. I wonder if anybody's found that. Hey, Mohammed, unmute. Have you found that little VF and that little VG, Mohammed?
No, I didn't find it.
Okay, that's fine. Mohammed, can you find table V.1.2?
I don't have the book.
Oh, I'm sorry, that's right.
Yeah.
You need to get the book. Now, some of the students got it direct from Wiley. Hey, you guys that got it from Wiley, did you have to give them a credit card to do that? Who's help me on this? Who got it from Wiley?
I did.
Yeah.
They had. I just paid with my debit card.
You paid with your debit card. You got to give them money. They're not going to give you this free, are they?
Right.
But you got the rental for $41?
Yeah, like 42, I think, for about 4 months.
That's a good deal. Mohammed, see if you can do that. You're going to need, you need to get the book, the ebook.
Yeah, I hope so. I will get it today.
I bet you can. I bet you guys can get it. Okay, now we're gonna plug this in and we're gonna find the specific volume. Notice we're not using the ideal gas because see, we're in here, guys. We're at a quality of 0.8. That's 80%. We can't use ideal gas in there. That's got liquid. It's kind of like that container that had the liquid and the vapor in it. Can't use ideal gas. I wouldn't even use that quality thing. No, don't use, the quality thing is sort of a refinement on the ideal gas. You don't use it on mixtures. But we can use this. Here we go. I'm going to use this. Here we go. This is 0.001177. This is 0.8. Now here, you would have to subtract these. But they've already subtracted for you if you can find it in the book. It's 0.001177. Well, no, wait, no. 0.09845. Now, if you subtract these two, you should get that. Let me see if you do. I'm going to subtract VF from VG and see what I get. Here goes. 0.09963 minus 0.001177, 0.09845, yeah, by Jove, I get exactly what they got. That's how they got that number. They call that VFG. Okay, now I'm going to plug this in and get my specific volume. Here goes. And we're going to take that 0.09845. Is that what they said? Yeah, 0.09845 times 8.8 plus 0.001177. I got an answer. I got 0.079937 cubic meters per kilogram. We just found the specific volume using the quality. Any comments or questions before we move on? Okay, we're going to move on. We have 10 minutes left. And what I want to do is I want to do a problem out of the book here. This is, we might have time to do this problem. It's from 246. And I need to erase all this. Here's your last chance to ask me something. I'm going to erase it. All right. We are looking at problem 246. It's a problem in your book. And it says a 1 cubic meter tank is filled with gas at a room temperature of 20 degrees Celsius and a pressure of 200 kilopascals. We don't have time to do all three, but we can definitely do part A. Part A is they want to know, they want us to find the mass if we're dealing with air. Okay. Well, what we're going to use is PV equals RT. And the pressure we know. Hey, look at here. We got that. R, well, we can look it up. It's in the back. And T, and now watch it. We got it, but it's got to be in Kelvin. Okay. And now that'll give us the little v, but it won't give us the mass. But hey, guys, the mass is equal to the volume divided by that little v. So we can get the mass. We have the volume. See, this is the volume. This is the temperature. Only we need this in 293.15. What do you think? I think so. Okay, well, let's plug that stuff in and see what happens. Here we go. P is 200 kilopascals. We're going to solve for V. Now, R, you'd have to go look it up. I only have 5 minutes, but I know it by heart. It's 0.287. But you might have to look it up. Yeah, let's go back here and look it up. It's on page it's table A.5. Man, we've run across that table A.5 a couple of times before. It's an important one, isn't it? Now the temperature is 293.15 K. Okay, here goes. Solve for V. I'll give you 30 seconds. See if you can get the specific volume for me. Well, I got an answer. I wonder if anybody got 0.42. You could round it off to 07 cubic meters per kilogram. And that now that we have the V and we have the big V, they gave it to us. They said it's 1 cubic meter. You can solve for the mass. Go ahead. I plugged that in and I got a 2.377 kilograms. Yay, we got it. Now they wanted us to do this same problem with argon. Hey, we got 4 minutes. Let's do it with argon. First, though, everybody happy with that? If you have a question on that, just ask. Air at the temperatures and pressures that we use in this class is an ideal gas. And you can use the ideal gas equations. Where you have to use that, the tables, is if you have a mixture of maybe liquid and vapor, or if you got temperatures and pressures that put you give you answers so far off of the ideal gas, you could use the compressibility. But the rule is, if you have tables, use the tables. That's the best model we have. Okay, let's do this one here. We got 3 or 4 minutes. Let's do this one with argon. Here we go. Same temperatures and pressures. If you just woke up from a daydream, we're doing problem 246. And this time we're going to do argon. And everything is the same except this number here is going to be different. And you're going to get a different answer here. And you're going to get a different answer here. Okay. Somebody dig around and find what the gas constant is for argon. So start digging. See if you can find it. Argon. Probably A5, you reckon? That A5's got everything on it today that we've used. Yeah, it's A5. I'm getting 0.2081. Okay, we're going to put that in here because what we had before was for air. This is argon. Okay, now we're going to solve for the specific volume. Here we go. Well, I got an answer. It's different because that was air there, but we're doing argon now. I'm getting 0.3050. So we have a different specific volume, but the volume's still 1 cubic meter, so we can solve for the mass. I wonder if you're getting this. I'm getting 3.278 kilograms for the mass. And that is correct. They also wanted us to do propane, but that's okay. If you understand all that, you could do propane, I have no doubt. Well, it's sad, but our time together is drawing to a close. Do you have any last comments or questions for me?
I have one question.
I have a question about the homework.
The homework? Yeah, you got some homework due tonight, and you got some due next Monday night, and you'll find it in won't it be under the schedule? Click on schedule. Pretty sure that's where it's at.
I know where to find it, but I had a question about how to work it.
Oh, which one?
1B, the interpolation page.
Oh, yeah. Well, I think I asked you to I think I gave you 4 questions. Didn't
Right.
I? Yeah. I want
got-
you to go
I
ahead.
was a bit confused because I was looking at the table
Yeah.
and used those numbers and got a different value than if I used the table that was on the sheet.
Oh, did I goof up and give you the wrong numbers on my sheet?
I used that and I got something very different.
Oh, gee, I wonder if I goofed up and gave you the wrong number. I'll look at that. Is this Parker? Is that who I'm talking to?
Spencer.
Spencer. Spencer, use the numbers on my sheet. Okay.
Okay.
But you looked up the numbers in the tables and you say they're different than the numbers on my sheet?
Yeah, well, yeah. If
Okay.
it did some, using the difference for the temperature from the table you gave us, and then extrapolating that to the temperature we needed to solve for.
Yeah.
I got something about something that was very different from finding the answer in the table.
Okay, well, let me help you on that. There were 4 problems, right?
Yes.
Okay. And which problem are we talking about? 1, 2, 3, or 4?
It's 1 and 2. 3 and 4 were separate.
3 and 4 you're okay with,
Right.
but 1 and 2 you have a problem with.
Yes.
All right. And did I give you I don't know, I don't remember. Did I give you a table, or do you have to look it up in your book?
There's an example table that has it.
Okay. Now, I need to look that up and see what you're talking about there. Number 2 is also the same way?
Number 2 is just an extension of that with numbers that aren't on any table.
Uh-huh.
So, if I use the table that's provided, it's got 3 temperatures, 2 pressures, and we find the 3rd pressure in between.
Yeah.
And then I used that to find the change per degree increase.
Yeah.
And used that to find what we needed to find on question number 1. But then when I compare that against the numbers in the book, the pressures that we'd be using are extremely different.
Wow.
For the pressure that I calculated for 114 degrees using the stuff from the book,
Yeah.
I got around 164, but using the table you provided, I got around 17.
Okay, well, let me look up the water for 114. Just a minute. Going back in the back here, we're trying to answer Spencer. It's Spencer, isn't it? Isn't that who I'm talking to?
Yes.
Trying to answer Spencer's question. And if you look up 114 in the back, 114 Celsius. They don't have 114. They have a 115. That's pretty close, right?
Right. I used the 110, 115 to find what it would be at 114, and that was
Right.
around 164.
Yeah. Well, it's very close to 164.
Yeah.
In fact, that answer would be acceptable to me. 164 sounds good to me, Spencer. And now, what but I gave you some numbers that were different.
Yeah, looking at the paper you gave us,
Yeah.
it shows like the pressure at 20 degrees being 2.339, at 25 being 3.169. And if I used those differences to extrapolate over to 114, the pressure I ended up with is around 18.
Now, did you say 20 degrees Celsius?
Yes. That was in the example at the top of the page. I wasn't sure if that was just something you wanted us to work with, or if that was just an example.
I thought I asked you to find water at 114 degrees.
You did, but at the top of the page, there's an example.
Yeah.
That you ask us to work through and solve.
Yeah, that's at like
and
20
that just,
degrees.
I guess.
That's just an example.
Okay, that just really threw me off because the numbers are very different from what's
like,
actually in the book.
Oh, they're different than what the book has?
That's what I remember from working it last night.
Well, look at this way, Spencer. It's Spencer. I'm talking to Spencer. And
yes.
you got the right answer, Spencer. You got what'd you say you got for number one?
163.94.
That's what I got.
Okay.
So you're okay. You're okay.
Okay, then I just need to rework number two because I did that one wrong.
Oh, okay. Anybody else before we say goodbye?
Where do you turn in the homework at? I don't see where.
You have to send it in to me on Blackboard. You have to be in Blackboard.
Right.
And you have to send it to me on Blackboard. Now, if you have a scanner, you can make a file and send me the file. I'll click on the file and up comes your homework. Does that sound right?
Well, I don't see a place to upload the file at.
Click the actual assignment, like where it says assignment number 1B, and then you can submit it once you get into that page.
Yeah, did you hear that? Click the assignment, 1B.
It just brings me to Word.
Well, not the assignment, the part above it that says assignment number 1B, not the interpolation.doc.
Oh, I got you. Okay.
I'm not very red hot on this computer stuff, guys. We'll figure it out though. Any other last comments or questions?
I have a question related to, are we going to be provided tables for exams and stuff?
No, you're going to have to use the tables on your ebooks.
Okay.
Yeah. And
I didn't know if we were going to be allowed to use those in an exam.
Absolutely. It's an open book, open ebook. You bet.
Gotcha. Okay.
Next, anybody else? Well, okay.
I have one quick question for doing the homework. Whenever we do it, do you want us to just like edit the Word document and then send it in that way, or do you want us to like actually print it out and like handwrite everything and then send it back in?
I guess either way would work. If you read the directions on my syllabus, I like my homework done on engineering paper, and I like for you to print out or write out the question exactly as it is in your book, and then you need to submit it to me on Blackboard through the I'm just not very good with the terminology.
Okay. I believe my question got resolved with that. Thank you very much.
Good, and I will put the key on Blackboard after I get your submissions, so you can tell why your grade is a 4. 4 is perfect. If you don't get a 4, read my key and you'll know why. Well, guys, I won't see you till Monday at 8:30, right? But we'll suffer through this. Okay, 5, 4, 3, 2, 1, blast off. Bye-bye for now.